Hello everyone. In this session, I'll be presenting a work titled Unlocking Wordline-level Parallelism for Fast Inference on RRAM-based DNN Accelerator. I'm Yeonong Park, a PhD student at Seoul National University under the supervision of Professor Jae Lee. My main research interests lies in memory systems and hardware-software co-design for emerging applications. I'll begin with a brief introduction on RRAM-based memory matrix multiplication. RRAM is a type of non-volatile memory that stores data by programming cell resistance. Usually, RRAM is organized in the form of Crossbar arrays. RRAM Crossbar arrays is highly dense, fast, and energy efficient in memory matrix multiplication engine. Since matrix multiplication is a key primitive of DNN computing, many RRAM-based DNN accelerator architectures have been proposed for the past few years. This is a build line of RRAM Crossbar arrays, which is approached in memory dot product. Two cells are programmed to have conductance of G1 and G2 respectively. When voltages are applied to word lines, according to Ohm's law, the current flows through the RRAM cells as much as the multiplication of the applied voltage and the cell conductance. The currents flowing through the cells are accumulated through the build line. The resulting build line current is the dot product between vector V1, V2 and vector G1, G2. Extending this concept, MAW and Crossbar array can execute the matrix vector multiplication between a vector of size M and an MAW and matrix. For this purpose, Wordline driver drives the value corresponding to the vectors to be multiplied, and MAW and RRAM Crossbar arrays store the values of MAW and matrix. The resulting build line currents are reached in sample and hold circuit and then converted to digital signal by analog to digital converters. Ideally, each RRAM cell can represent arbitrary number, and Wordline drivers can drive arbitrary voltage level. However, for efficient hardware implementation and noise resiliency, practical designs usually utilize a single-level RRAM cell which has only two states, on and off. To represent the multi-bit value, each value is bit sliced on multiple bit lines. Also, Wordline driver usually support only binary logic levels and feed multi-bit input in a bit serial manner. As this way of computation produces many partial sums corresponding to each bit position, a shift and add unit is necessary for partial sum accumulation. RRAM-based DNN accelerator improves its performance by exploiting various levels of parallelism. The most straightforward way is to have mirror arrays execute computation in pairs. But this way incurs increase of area and power overhead proportional to the throughput gains, as it requires not only more crossbar arrays but also more peripheral components. Another way of performance scaling is to process more bit lines at a cycle. This way does not increase the number of crossbar arrays, but it requires more ADCs and more shift and add units because more bit line currents come out every cycle. The best way of performance scaling is to process more word lines at once. This way does not need any hardware components to be replicated. Instead, as possible output range expands, wider ADC and wider shift and add units are necessary. This is quantitative comparison of the three performance scaling strategies. Exploiting Wordline-level parallelism achieves the same amount of throughput gains with notably lower area and power overhead compared to the other strategies. However, there are challenges to overcome to exploit Wordline-level parallelism. The problem is that parcel deviation accumulates more along the build line current as the more word lines are activated. In other words, the more we exploit Wordline-level parallelism, the more likely the readout errors of build line current occurs. There are two major sources of build line current deviation that increases with the number of activated word lines. First one is high resistance state cell current. When using single level cells, cells representing logical 1 are programmed as a low resistance state, and cells representing logical 0 are programmed as high resistance states. Low resistance state cell, or LRS cells, pass a certain amount of current when activated, which we call IRS. And ideally, to represent logical 0, high resistance state cells, or HRS cells, should not pass any current even when activated. However, in practice, HRS cell pass non-zero current as much as IHRS. The ratio between IRS and IHRS is called on-off ratio, which we denote as alphabet R. When on-off ratio is small, the impact of unwanted current shift by HRS cell current becomes significant. This example shows how HRS cell current can cause readout errors. Let's assume a build line with 4 cells, of which only one cell is programmed as LRS and the other 3 cells are programmed as HRS. On-off ratio is 3. 2 different input sets are fed into this build line. The correct readout output of the left case is 1, as a cell representing logical 1 is activated. Meanwhile, the correct readout output of the right case is 0, as only cells representing logical 0 are activated. However, the build line current of these 2 cases are same. There is no way to distinguish these 2 cases, although they should output different readout result. At least in one of these 2 cases, the readout error occurs. Such an impact of HRS cell current increases with the number of activated word lines. Secondly, RRAM cell resistance randomly varies cycle to cycle. The resistance of RRAM cell is known to follow log normal distribution characterized by the resistance value and the resistance deviation. Impact of such per cell resistance deviation obviously increases with the number of activated word lines. Here is the experimental study on the relationship between wordline-level parallelism and reliability. As we increase the number of word lines to process in pairs, or the maximum number of activated word lines, which equal MAW, end-to-end DNN inference accuracy drops. Accuracy drop becomes more permanent with lower on-off ratio and higher resistance deviation. Therefore, to maintain inference accuracy, RRAM-based DNN accelerator limit MAW to a much smaller number than Crossbar size. For example, recent RRAM prototype chips only activate 8 or 16 word lines at most among few hundreds of word lines. In this way, reliability issue limits the performance. Therefore, we propose 2 key techniques that improve performance of RRAM-based DNN accelerator by increasing MAW while minimizing accuracy degradation. First, we propose input-aware current compensation, which is a technique that mitigates readout errors by eliminating impact of HRS cell current. Second, we suggest a systematic approach to determine MAW for each layer to exploit non-uniform MAW across the network. Now I will explain the 2 key techniques in detail. Input-aware current compensation, or IACC, targets to eliminate unwanted effect of HRS cell current on bitline current. As key insight is to dynamically compensate resulting bitline current as much as it is perturbed by HRS cell current. This is a problem formulation. We denote the number of activated word lines as n, and we assume that L among n cells are in LRS, while H among n cells are in HRS. For sure, L plus H is n. Then the equation for the resulting bitline current is L times IRS and H times IHRS. Our mission is to eliminate the term H and obtain correct L. For example, in this case, 3 word lines are activated. So n is 3 while MAW is 4. L is 1 and H is 2. The resulting bitline current is IRS plus 2 times IHRS. The most straightforward way to eliminate H from bitline current is to simply subtract H times IRS from the bitline current. Then only L times IRS is left from which we can read out L correctly. However, subtracting H times IHRS is fundamentally infeasible. H is a value which is available at the readout, so we take different approach. Instead of H times IHRS, we propose to subtract N times IHRS. The equation for the bitline current can be rewritten as this. If we subtract N times IHRS from here, L times IRS minus IHRS is left. Since IRS minus IHRS is constant terms, we can correctly obtain L from this value. Subtracting n times IHRS is feasible, but this is because n is simply the number of ones in input vector, which we can figure out before without. Then the remaining question is how to dynamically generate the current n times IHRS for subtraction in an efficient way. For this purpose, we add an extra build line, all of whose cells are programmed to HRS, like this. Then the current flowing through this build line becomes n times IHRS, which is exactly what we want. We add current subtractor between sample and hold circuit and ADC, so the subtraction results are fed to ADCs for without. On top of IACC, we also propose layer-wise MAW selection. Different layers in the same network exhibit different amount of errors for the same MAW. Also, errors on different layers have a varying impact on the end-to-end accuracy. Such properties of DNN remain a chance to improve performance by layer-wise MAW selection. Then the issue is how to determine MAW for each layer. We basically suggest a two-phase process which consists of profiling and iterative search. During the whole process, user parameter called target accuracy loss level plays key roles as it designates the upper bound of validation accuracy degradation. The first phase is profiling. We profile marginal cost of each layer's MAW. I will explain it by giving an example. This example illustrates the profiling process of the first layer of 4-layer network. For this purpose, we change MAW of the first layer while the other layers run in a pure software mode. Then we measure accuracy deviation from the ideal end-to-end accuracy for each MAW, which is labeled as def. Note that it is not drop but deviation, so we use the absolute value of the difference. Next, we calculate marginal cost of each MAW by comparing the deviation with that of the immediately previous level. The marginal cost of the smallest MAW is not defined. Also for the other layers, the same process goes on. After finishing profiling, iterative search begins. For search, we define a sequence of state. A state is a tuple of MAW of each layer. The initial state is defined as a tuple of default MAW. The following states are defined by increasing the MAW of a layer that has the smallest marginal cost. For example, in this case, layer 4 has the least marginal cost, so increase MAW of layer 4 by 1 level for making state 1 from state 0. State 2 is defined by increasing MAW of the layer 4 again, as it still has the least marginal cost. And state 3 is defined as A16832, as the layer 2 now has the least marginal cost of increasing MAW. We continue this process until all the states are defined. After defining a sequence of states, we now have to determine which state to use among them. Basically, we advance state following the sequence order as far as the simulated validation accuracy does not go below the target accuracy. To reduce computation, we perform binary search. For example, let's assume that ideal accuracy is 93.5 and target accuracy loss level is 0.5. For the first round, we advance as half of the total states and arrive at the state 4. The validation accuracy is higher than the target accuracy, so we still can move forward. We advance further as much as the half of the remaining states and arrive at state 6. In this time, the validation accuracy drops more than the target loss. So in the round 3, we move backward to the halfway point between the current state and the last visited state, which is state 5. We repeat this process until we cannot move anymore, and the resulting policy would be the last one that satisfies the target accuracy loss. In this example, the state 5 is the final result. There is one important design issue for layer-wise MAW selection. Different MAW implies different upper range. For example, for MAW 8, the output range would be from 0 to 8. Similarly, the layer with the largest MAW, which we denote as alphabet M, would have much wider output range, which is from 0 to M. The different MAWs necessitate different ADC resolution for lossless conversion, like this. In such a case, how we should set ADC resolution? It is impractical to ADC resolution differently for each layer at a design time. The most conservative way would be using log M plus 1 bit resolution, considering the maximum MAW. However, while this conservative choice can minimize accuracy degradation, it increases ADC latency, which may compensate the performance gain of our techniques. So our suggestion is to use log M minus 1 bit resolution ADC. And when bit line current exceeds the supported range, we just clip the signal. For MAW of M over 2 or M, such a case can happen, but the chance is really low. We now move on to evaluation. To estimate the impact of input-aware current compensation, we estimate end-to-end inference accuracy with a custom simulation, and we assume a generic RRAM-based DNN accelerator architecture. Here is the result. With IACC, the accuracy remains fairly high with the increased MAW. However, even with IACC, for SciPar 100 and tiny ImageNet dataset, the MAW cannot increase much. So we apply both IACC and layer-wise MAW selection and estimate its speed up over the baseline. We set target accuracy loss level as 1% and use MAW from 8 to 128. We perform the same experiment with different ADC resolution to see its impact. Across all workloads, we achieved substantial speedup. The speedup is especially high with the recommended ADC resolution. In summary, we introduced two key techniques that can boost up inference performance of RRAM-based DNN accelerator by increasing wordline-level parallelism. First, we demonstrate the effectiveness of wordline-level parallelism. Then we propose an effective yet lightweight method to mitigate bitline readout error. And also, we introduce a systematic way to find optimized MAW for each layer. These two techniques lead to substantial throughput gains with a minimal area and power cost. Thank you for listening.